show. Does everyone have their notes open? 5.4. So, complex numbers. We're going to get more complex today. So much excitement. All right. So, we've been dealing with complex numbers. We've defined them, right, as a real part and an imaginary part. So we have that a plus bi that hopefully you guys kind of are getting the hang of, where I is the square root of -1. So we're going to start off, we're going to talk about graphing complex numbers. And this is going to sound confusing, but I want you guys to think of this very similarly to how we've been treating graphing points in an xy plane, okay? So we're going to graph complex numbers, and we're going to use this notation that you see right here, this a comma b, change my pen, where a is going to be the real number, and b is going to be the imaginary number. Okay? And we're going to graph these points similar to how we graph xy points, like we've been doing for a while now, except we're going to graph them on what we call the complex plane. Okay? And similar to how we have an x-axis and a y-axis, we're going to have a real axis and an imaginary axis, just like how xy correlates with a and b. The xy axis is going to correlate with that real and imaginary axis, okay? And we're going to call this the complex plane. So, if we have a complex number, let's start out with our first complex number. If we have -1 plus 2i, where would we graph this point if we were to transition it into how we've been notating it? So we're going to have our xy similar. It's going to be that a, b, where a is the real part, so we have -1, and b is the imaginary part, which is that 2i. We're just going to write 2, though, because we know that that part is imaginary. Okay? And then when we graph it, just like you guys have been doing in the xy plane, we're going to graph it at -1, +2 on the axes. So it'll show up right there. Okay? So we're going to graph a few more points just so that we can get the hang of this. So we're going to have -2 minus I. Can someone tell me what the notation is for this? How we would write it? -2, -1. Perfect. Thank you. And then we would graph that just the same. -2 on the real axis, -1 on the imaginary axis. Then we'll do 2 more real quick. 1 minus 2i. And that's going to be 1 comma -2, which is down here. And then we're also going to have 2 plus I. So it's going to give us 2 comma 1. Right there. Okay, so if we were to graph just the letter I, where would it be? It would be right here on our imaginary axis, right? Because there's no real part, it's just the imaginary number. So this would translate to 0 comma 1. Now if we just had the number 1, or actually sorry, if we had I squared, what's I squared equal to? And so how would we put that in mapping notation? Is -1 a real number or an imaginary number? -1 is a real number, so we're just going to put that for the real part. And then we've actually gotten rid of the imaginary part by squaring it. And so we're going to have -1, 0 right here. And then if we multiply that by I again, so I cubed is going to be I squared times I, which is -1 times I. equals negative I. And we're going to map that at 0, because there's no real part, only the imaginary part, negative I, down here. Negative I. So we have I is just I squared we know is negative 1. And if you multiply by I again, you're going to get negative I, right? And if this is I right here, this is I squared, this is I cubed, where do you think I to the 4th is going to be? It's going to be right at the 1, right? So as we're multiplying by I again and again, it's just going to keep going in this circle. You see that? So it's going to go I, negative 1. Yes. Mm-hmm. Oh, yes, I'm sorry. Someone did say that. Someone did correct me. Apologize. Now I see what you're saying. Yeah. And then I to the 4th would be I squared times I squared, which is negative 1 times negative 1, which is 1. Okay? So I know this sounds a bit confusing, but what we're basically just doing is taking any complex number and saying there's a real part and there's an imaginary part, and we're going to graph what those parts are. And we're going to add in a new vocabulary term here. We're going to call it the modulus, okay? So the modulus is the distance from the origin on the complex plane to the point, okay? And while that might sound confusing, you guys have all, or at least most of you, have taken geometry, right? And in geometry, when we have a triangle, so let's take a triangle here. If we have A, B, and C, we know that to find the length C, how do we get that? Yeah. A squared plus B squared equals C squared, which means C is equal to the square root of A squared plus B squared. And so when you look at the graph that we've made, if we want the distance from the origin out to this point, that's really just the length on the real axis squared plus the length on the imaginary axis squared and the square root of that, just like how we solved in geometry. We're going to treat it just about the same. So we'll say that the modulus, I'm sorry, my spelling is terrible. What happens when you're an engineer? So the modulus for a complex number, a plus bi, is equal to the square root of a squared plus b squared. And how we notate it, just for how we write it, is we write it basically like the absolute value of a plus bi. Because we say it's the distance, always positive, the distance away from that origin point. What questions do you guys have so far? I know it's a little bit different, but it'll start to make some more sense. So to find the modulus here for A, we're going to identify our parts. So we say A equals negative 3 and B equals 4. And then we're going to take that square root of negative 3 squared plus 4 squared. Okay? And that's going to be the square root of 9 plus 16, which is the square root of 25, which equals 5. Now, what do you guys notice is going to happen to the signs for A and B? When we look at the equation for how we calculate the modulus, a is going to be squared and b is going to be squared, which means the signs, when we're calculating the modulus, they won't actually matter, right? Because when we look at this one, so this is, we've just switched the sign from here over to here. And when we do this, we're still going to have the square root of negative 3 squared plus negative 4 squared, which will give us the square root of 9 plus 16. So we're going to get the exact same modulus even though the sign is switched. And I want us to see that up here. When we look at our graph, and we have this, so when we look at these 2 points right here, this one and this one, they're going to be the same distance from the origin, right? You guys see that? When we think about it in terms of geometry, that length right here is going to be the exact same as that length here. And so even though we flip the signs for A and B, for these 2 points, 2, 1, and negative 2, negative 1, we switch the signs, they're going to be the exact same distance. So they're going to have that same modulus. So for 2 plus 4i, we're going to do the same thing. Take the square root of 2 squared plus 4 squared, which gives us the square root of 4 plus 16, which is the square root of 20. And remember, guys, we need to simplify our radicals, okay? That was something on our exit slip the other day. I don't think a single person simplified. Actually, this class there were a few, but in the other class I think there were 0 of people simplifying their radicals. So instead of square root of 20, we're going to factor out that 4 and say this is the square root of 4 times the square root of 5, which is equal to 2 root 5. And then like we said, this one, since we can see that it's just the sign flip, and we know that doesn't matter, we know that it's going to be the same answer. Because it's going to be that same distance away from the origin, okay? So quick review, if we have a number, complex number, a plus bi, what's the conjugate? Yeah, the conjugate is going to be a minus bi. We flip the sign only of the imaginary. That's an important distinction. We're only going to flip the sign of the imaginary part, okay? Now, question. Will conjugates always have the same modulus? What do you think? Who thinks yes? Raise your hand. Will they always have the same modulus? About a third of people are saying yes. Yeah? So are A and B, what's the difference between this one and this one? Yeah, we're flipping the sign of the B, but what did we just talk about up here about the sign? Same distance, right? Which is that modulus term that we're talking about. And so conjugates will always have the same modulus. Because those A and B terms, even though the sign flips for the B, they're going to have the same value once we square them, okay? This modulus isn't referencing positive or negative. And what do you guys think will happen when we multiply a complex number by I? Do you think the modulus will change or will it stay the same? Stay the same? What do you guys think? Who thinks it'll stay the same? Nobody? Two or three people? So it will also stay the same. But I want to walk you through a few of these. So we're going to shrink. So up here, when we had these points, when we went through with I, right, what happened when we multiplied I by I? So we started with I, and then we got I squared. And it just rotated from here to here, right? And then we multiplied it by I again, and went to here, and then back to here. And it keeps going around. It's just rotating around, okay, right? And the modulus is staying the same. And we're going to see, as we do that with other terms as well, so if we take this first point and multiply it by I, so we have negative 1 plus 2I. If we multiply that by I, just put I on this side, we're going to get negative I plus 2I squared. And we know I squared turns into negative 1. We get negative I minus 2, or negative 2 minus I. Put it in our standard form. And if you look, we've already graphed this point. Negative 2, negative 1. We've already graphed that point. That's point 2 right here. And so if we were to label these points in order that we've done them, what we did here, each time this number multiplied by I is going to be this, multiplied by I, multiplied by I. And so what we're going to see is this going to keep rotating around. When we multiply by I, it's not going to change the modulus at all, so that home distance that we keep talking about, away from the origin, it's just going to keep rotating, just like we did with I squared, I cubed, I to the fourth. Okay? All right, a little bit more review. So what happens when we multiply complex conjugates? So what we're going to do, we're going to leave it in our general form that we've dealt with, okay? A plus bi, a minus bi. So we can see that these are conjugates. Left in general form. And so when we use FOIL to factor these out, we're going to get a squared for the first term. The outside term is going to be minus a b I. The inside term is going to be plus a b I. And then we're going to get minus b squared I squared. And what is I squared? I squared is negative 1. And so this term is going to become plus b squared. And what do you see about these two middle terms? They're opposites. So they're going to cancel each other out in net 0. So we're going to be left with a squared plus b squared. What do you guys notice about this? Do you guys see an imaginary part in there? There's no imaginary part of this term. A squared plus b squared is going to be a real number plus a real number. And so when you multiply a number by its conjugate, we get a real number every time. This is going to be a very useful tool for us in a minute. So when we learn new ideas in math like this, when we learn things like, oh, a conjugate pair multiplied together is going to give us a real number, what we want to do is we want to remember that, and we're going to store that in our mind, kind of like a tool. So Beth's given you guys kind of her math tool belt, right? This is something we want to kind of add into that tool belt. We want to add these rules, different ways that we can manipulate equations. We want to store those away, and then we're going to use them at different times to solve equations, all right? So when we have an equation and we do something to one side of the equation, what do we have to do? We have to do it to the other side. An equation always has to be balanced, right? So if you multiply one side by 5, you have to multiply the other side by 5. We've kind of made two exceptions to that. Two things that we do that we're allowed to do to one side and not the other. So we can always add to one side a total of 0, right? Because if we add 0 to an equation, does it change anything? No. And so we've been using this when we do complete the square, right? If you have y equals x squared plus 4x plus 5, what we've been doing is saying, okay, if we want to get this into vertex form, we're basically going to add a 0 by adding a number and then subtracting that same number. So what we've been doing is saying y equals x squared plus 4x plus 4 minus 4 plus 5. And then what we do is we factor that and we say y equals x plus 2 squared minus 4 plus 5, right? What we've done is we've done this step right here where we add a net 0. That's kind of one of our tools that we've been using as we've been working with quadratics to get an equation into the form that we want it to be in, that's easier to use or useful for a different purpose. Another thing we've been doing when we deal with fractions is we can always multiply one side by 1, right? Because when you multiply something by 1, it doesn't actually change its value. And so this is another tool that we've been using. So if you have fractions that have different denominators, like we have here, we have a 14 and we have a 7, and we want them to be similar, what we've been doing is taking this 7th and multiplying it by 2 over 2. Because 2 over 2 is equal to 1, right? But what it does is then it gives us common denominators so that we can add them together into one term, okay? So I want you guys to think of each of these as tools, okay, that we've been using already in math, and now we're going to apply them in a different way, okay, with complex numbers. So take a minute or two, guys, and talk at your table. I want you guys to wrestle with this a little bit. Work at your table. How can we, each of these complex numbers, we want to get to move into the form a plus bi. We don't want I in the denominator. When I is in the denominator, it's harder to work with. It's not a standard complex number. We want to switch it. How can we do that? So I want you guys to talk at your table, talk through how might we be able to move this complex fraction into a normal complex number and get I out of the denominator. I've given you guys a bit of a hint, all right? Talk amongst your table, guys. Use each other. Yeah. This is the confusing part of the problem. It sounds dumb, like I said on Wednesday, like it does have applications that get used, and weirdly didn't get used until I had to do that. But it is a form of mathematics. What? Yeah. I won't say that you will use it. I will say that this. Well, it helps them to model. No, I'd take one. You can't go example. So think about how you might get rid of I. Yes, sorry. Is anybody coming up with an idea at their table? Do you think it's working? What do you guys think back there? Any ideas? We can multiply by conjugate, but so
Yeah.
you can't multiply by whatever you want, because otherwise you change the value. So we can multiply by one. Right? So how can you make this? You guys making any headway? Yeah. Very close. Very close. So what is this problem? You're trying to make this well. Real. Okay, guys. So a few of you were getting close to this. So what we're going to do is we're going to take a few of those tools that we've learned, right? So we want to get I out of the denominator here. So what we're going to do is we have 3 minus I over 2 minus 2I. And we're allowed to multiply any number by 1, and it doesn't change the value of the number. So we're going to multiply it by 1, which sounds unhelpful. But any number divided by itself is what? 1. And so we can basically say we're going to multiply this by some number over itself. And putting that together with our other tool that we just learned, tool number 1, what happens when we multiply complex conjugates? We always end up with what type of number? A real number, and that's what we want in the denominator. So what we're going to do is we're going to say, to get this portion to real, we have to multiply it by its conjugate. So we're going to multiply by 1, but that 1 is going to be the conjugate over itself. Okay? You guys see where I'm going? So now when we multiply this denominator out, so I'll do the denominator first because that's what we care about. We're going to get our first terms. So we're going to get 4. I'll put parentheses so we can see that we're distributing around across. We're going to get that first term, 4. The outside is going to give us plus 4i. The inside is going to give us minus 4i. And the last term is going to give us minus 4i squared. And then the top, we'll get 6 plus 6i minus 2i minus 2i squared. And now you see in the denominator, these two I terms in the middle, they're the opposite, like we talked about before. They're going to cancel each other out. So you're going to be left with in the denominator 4 minus 4i squared, which we know what I squared is, right? Negative 1. And so now we've shifted our denominator into a real value. And on the top, we're going to keep simplifying. 6 plus 6i minus 2i plus 2, because it's 2 minus 2i squared. That I squared term, whenever we see that I squared, we need to replace that with negative 1. Okay? So that's why this negative 2i squared becomes plus 2. And what this will give us is 8 plus 4i divided by 8, which equals, and we're always going to separate out the two terms. So this is going to be 8 over 8 plus 4 over 8I, which equals 1 plus 1/2 I, okay? So by using these tools that we've learned, we've been using these tools, right, and learning, when we multiply conjugates, we get a real number, and you're always allowed to multiply something by 1. We're using those tools in our tool belt that we're acquiring over the course of really all math that we've learned. And we're simplifying this number that has I in the numerator and denominator and looks complex, or difficult, I should say. And we're simplifying it down all the way into this term here. It's just 1 plus 1/2 I. So we're going to do this again for part C. I'll work out C and then I'll have you guys try B on your own. So for C, what would we multiply this by to simplify it down? 3 minus I? Yes, 3 minus I over 3 minus I. And that'll give us 9, minus, this is the denominator I'm working on. 9 minus 3I plus 3I minus I squared on the bottom. And on the top we'll have 12 minus 4I plus 3I minus I squared. Move this so that there's a little more space. And then that will simplify down to 12 minus 4I plus 3I plus 1 over 9 plus 1, which is going to be 13 minus I over 10. And that's going to be our complex number. Every time we simplify, we want to make sure we break it back down into our real terms and our imaginary terms. We don't want to leave it all over one denominator, even if that's a step in the process. Because we want it in this notation so that we can label it later when we graph it or something else. This gives us our 13 over 10 comma negative 1 over 10 if we were to put it in mapping notation or to solve for the modulus that we were talking about before. Okay? We always want to leave it in this notation. So I want you guys to try B on your own, and then I'll go through it real quick. You look confused. It's okay. So again, we want to keep getting used to this I squared. When we see I squared, we know I squared is negative 1. And so whenever we see that, we want to convert it back to what we know, a real number. And we're getting those real numbers in the denominator so that we can simplify these terms. I know imaginary numbers are a strange thing to work with, but part of what we got to learn in this class. So that's all for complex numbers today. You guys have homework questions? We have a little bit of time to go through those. Yeah.
Mm-hmm.
Number 9. This will be posted online too, so if you need to go back and see those. A4 homework, right? Number 9.